Welcome to physics class on alternating current part 2. In the part 1, the previous video we have done about electric EMF and current, average or mean value of AC EMF and current, and root mean square value of alternating EMF and current. And in today's video part 2, alternating current part 2, we need to discuss about the AC circuit with resistor, AC circuit with inductor, and AC circuit with capacitors. Let's see about the AC circuit with resistor alone. Why we are doing this AC circuit with resistor, inductor, and capacitor alone? This is because to do that AC circuit with series LCR circuit. So first we need to discuss about the resistor, inductor, and capacitors alone, and then we will come to that AC circuit with series LCR circuit. So first let's try to do about the AC circuit with resistor, inductor, capacitor separately or individually. Okay, now let's start with the AC circuit with resistor. Now in AC circuit with a pure resistor, the circuit diagram will be like this, and we know that this represents resistor and it is connected with the source of EMF, and that source of EMF is nothing but this is AC, and let that instantaneous EMF of this AC source be denoted by E is equal to E naught sine omega t. Now we know that from Ohm's law that current is defined as what? Ratio of what? Potential difference to that of the resistor, right? Now this potential difference, in our case here, we need to take it that instantaneous EMF here. So your instantaneous EMF will be acting just like the potential difference across this R. So at any instant, the potential difference across the resistor will be taken as the EMF. That means the instantaneous EMF. So E by R is equal to what? Your instantaneous current. That means current at that instant. So this, instead of this instantaneous EMF, let's replace it by E naught sine omega t, so that it will be E naught by R sine omega t. Now you can express this as I is equal to E naught sine omega t. Why? Because this is the peak EMF divided by resistance. So even though this is what a peak EMF, this is also just the potential difference. So potential difference divided by R, as it is peak, so the current will be also peak or maximum, you can say. So we can express as I is equal to I naught sine omega t, where I naught is equal to what? E naught by R, and R, it can be also expressed as E naught by I naught. That means your instantaneous, okay, EMF divided by the instantaneous current, that will be also equal to R, no doubt. But here also what happened, your ratio of peak EMF to the peak current, that will also give you the resistance. Now from here we can find it out that your, from these two relations, that E is equal to E naught sine omega t and I is equal to I naught sine omega t, both are the instantaneous value of EMF and current. And from these two equations, that sine of omega t are involved, and moreover they are in phase. If there is some additional term here, just like that plus pi by 2 or minus pi by 2 or whatever else, minus phi, then that phi or pi by 2 that is coming up here, by observing that phase, okay, we call it this omega t as phase. So by observing the phase in both the equation, we will have to judge it whether this E advance or I advance, or in both cases, if something is there plus something phi, then we will say that I leads, the instantaneous current leads the instantaneous EMF. But as there is no plus phi or minus phi here, nothing here, so that means the phase are same. So we say that EMF and current in AC circuit containing a pure resistance are in phase. Got it? So what happened? We say that instantaneous EMF and instantaneous current are in phase in a circuit containing pure resistor. Now I'm just giving you again the same equation, so as make you to understand when we go further. Okay, that means your instantaneous EMF and instantaneous current are again written here. Now if you are going to draw the sinusoidal waveform of that, E is equal to I naught sine omega t, I is equal to I naught sine omega t here, then the red, okay, graph is for the instantaneous current and the blue graph is for the instantaneous EMF. So that means when this both instantaneous EMF and current, they are in phase, means what happened when they are at a point, okay, at origin, let's take it. So what happened, they start increasing their magnitude as time goes. What happened when current increases, correspondingly your EMF also increases. When this current reaches the peak value, at that time what happened, your EMF will also reach the peak value. Likewise, they are in phase, means what, when one is increasing, the other will also increase in that same direction. When current decreases, what happens, your EMF will also decreases in the opposite direction. When the current decreases its peak value, that means here, or rather you can call it, this increases in the opposite direction, and if it reaches peak, at that time also your instantaneous EMF will also increase in the opposite direction and it will reach the peak at the same time. So that means your instantaneous EMF and instantaneous current are in phase. Now that is depicted here in the graph, okay. And now let's try to express these in terms of phasor diagram. What is meant by this phasor diagram? Now phasor diagram is nothing but a rotating vector that represents a quantity, okay, varying sinusoidally with time is called phasor. Now here you see both instantaneous EMF and instantaneous current, they are sinusoidally varying with time, okay. And if these sinusoidally varying with time, that this function, if it represents as a rotating vector, okay, as a rotating vector, then what happened with respect to time, I mean, then this will represent a phasor diagram. As I told you that a rotating vector, okay, that represent a quantity varying sinusoidally with time is called phasor. The vector is imagined to rotate, okay, with the angular velocity equal to that of the AC, angular velocity of the alternating current. Then what happened in the phasor diagram, what happened, the value of the alternating, okay, peak current and the peak EMF are represented by arrows, got it, and they are called as phasors. And if they are drawn, okay, onto the plane of x-axis and y-axis, okay, with the horizontal axis making with horizontal axis omega t like this with an angle, then this diagram will be called as phasor diagram. And we need to see it from this phasor diagram that whether this peak EMF and peak current, whether there is any difference in angle between these two rotating vectors, we need to see it, okay. And by observing from this phasor diagram, we can easily find out that whether this instantaneous EMF, or rather your peak value of this instantaneous peak value of the AC current or EMF, whether which one is advanced or lagging than the other, can be easily observed from this phasor diagram. But as I told you that in the case of AC circuit containing pure resistor, we have said that this instantaneous EMF and instantaneous current are in phase. So what happened, their peak value will be also having the same phase. That means they are lying along the same line. So from the reference axis, the phase is what, omega t, both for what, both for the current as well as for the EMF. So while drawing, what happened, we draw this rotating vector as a peak value of instantaneous current and instantaneous EMF. Now how to find it? These instantaneous current and EMF from these peak values of current and EMF. Now if you take projections of these rotating vectors I0 and E0 on any axis, it can be on this line or it can be onto this y-axis, okay, then it will give you the instantaneous value of these current and EMF. Suppose if you drop projection onto this y-axis from this peak value of this current, then it will be projecting like this, okay, along this direction I mean, then this will give you your instantaneous current. And if you drop what projection for that of your EMF from this peak value, then what happened, the projection this will give you your instantaneous EMF denoted by E. Got it? So this instantaneous value can be easily obtained from the projection of this maximum or peak value of current and EMF, okay, onto the y-axis. It can be done onto the x-axis also. If it is done onto the time axis or x-axis, then this will give you nothing but this will give you your instantaneous EMF. If you drop projection for current from its peak value, then its instantaneous value of this peak current will be denoted by this line, okay, and saying here this line and this line will be same, right? Yes. This is all about that of your AC circuit containing resistor. And now let's try to move to that AC circuit with a pure inductor. Pure inductor is a solenoid, nothing, okay, it is nothing but it is a pure solenoid. Now if this solenoid is connected to the source of EMF, as we did in the case of pure resistor, E is equal to E0 sine omega t, the AC source. So what happened, your induced EMF, okay, when AC source is applied here, of whose instantaneous EMF is given by E is equal to E0 sine omega t. Now in the case of AC circuit, we usually started from this equation. So this is very important. Instantaneous EMF is equal to E0 sine of omega t. We know that the alternating current can be expressed in the form of sinusoidal function, and generally we use the sine function. E is equal to E0 sine of omega t, like this, okay. Now we know that in the case of inductor or a coil, the induced EMF developed, it will be equal to L di by dt, right? Rate of change of current times its self-inductance minus gives this is a direction for the induced EMF, okay. The direction of the induced EMF will try to oppose the incoming AC source. So just to represent that, 1 minus is assigned, okay. So your induced EMF in the inductor or the coil is minus L di by dt, where L is nothing but this is a self-inductance of the given coil, okay. The given coil itself is also denoted by L, and its self-inductance is also denoted by capital L. So in order to maintain the flow of the current, what happened, the applied EMF must be equal to, okay, the applied EMF, and as it is induced EMF, what happened, the applied current or the applied AC EMF must be opposite to that of the induced EMF. So in order to maintain the flow of the current through this inductor, what happened, the induced EMF must be equal and opposite to that of the applied EMF or the applied AC EMF. Only when that applied AC EMF is equal and opposite to that of the induced EMF, then only the flow of current is maintained in this circuit, right? Yes. Now therefore, what happened, your induced EMF, okay, that will be equal to your applied instantaneous EMF. So it will be equal to what? Minus di by dt. Equal and opposite. So what happened? Your induced EMF, if it is equal and opposite, then minus of this minus will be what? Plus L di by dt. So this induced EMF will be equal to the instantaneous EMF applied. Then only what happened? The current can be maintained through this circuit, right? So your instantaneous EMF is equal to L di by dt. What is this instantaneous EMF? We know that E is equal to E naught sine of omega t, so you just replace it here, and let's try to find it out, this small change in current. Okay, so di, so your di will be equal to what? E naught by L sine of omega t into dt. So this is a small amount of current, okay, that is what? Changing into this what? Solenoid. Now if we if you try to find out the instantaneous current passing through the inductor, then we need to integrate this equation. Di is equal to E naught by L sine of omega t. Now when we integrate it, then this E naught, the peak value, the maximum value is always constant. Inductance of this what inductor or a coil, that is also constant. So as long as you are not changing this particular solenoid, each inductance or rather self inductance will remain same. So what happened? Your E naught by L, these are constant. So you take outside the integration and you try to integrate only this sine of omega t. When you try to integrate this sine of omega t, then what happened? We know that integration of sine omega t is minus cos of omega t, right? And if you try to integrate this angle again omega t, then another omega will be coming in the denominator. So in the denominator you will have E naught by L, okay, into omega times minus cosine of omega t. Now this minus cosine of omega t can be rewritten as sine of omega t minus pi by 2. Okay, by using which formula? You must be knowing that sine of A plus B, right? Sine of A plus B, right? This is nothing but this will be equal to sine A cos B plus sine B cos A. So if you use this formula and if you apply it, then it will be coming that formula, this. Suppose in sine of this, or you can use it instead of this, you can also I'm sorry, it should be cosine of, why? Because we are you can do it from here also, same thing. Okay, both are interchangeable. So if you use it this as A as omega t, A as omega t, and B as what? Pi by 2. But if you are going to use this sign, then it will be, let me write it as plus minus, okay? So that if this A is equal to omega t, B is equal to pi by 2, and if you apply it, then it will be what? Sine of what? Omega t, say minus pi by 2. You need to use that minus, okay? Then what happened? This will be sine omega t, right? Cosine of pi by 2. Cosine of pi by 2 is 0. 90 degree, cosine of 90 degree is 0, so it will be 0. Okay, this term will not come. Then we are talking about minus, so you take it minus. So the sine of omega t minus pi by 2 will be equal to what? Minus sine of 90 degree. Now B is 90 degree, so sine of 90 degree is 1. Cosine of A means omega t, so you will have cosine of omega t. So minus cosine omega t will be equal to what? Sine of omega t minus pi by 2. You can use it by using the formula of cosine of omega t. Okay, cosine of omega t from where? Cosine of A plus B, A plus minus B. Okay, cosine of A plus minus B, you can do it from there also. By what? You can use it this cosine of what? A plus minus B, like this. So cosine of A plus minus B is equal to what? Cos A cos B minus plus sine A sine B, like that. So if you use it that one also, you will get the same thing. Got it? Yes. Let's go further. Okay, now see here what happened. I told you that this instead of this E naught by omega L, we use it what? This as what? I naught. Why? Because this omega L is just acting like a resistor. Okay, resistor in the sense, not in actually resistor, rather it is opposing. This inductor is opposing the AC current to flow through it, and this omega L is equal to what? XL. What is this XL? We call it this XL as what? Inductive reactance. That means the inductor offers some opposition to the flow of AC current, and we call it that opposition to the flow of AC current by the inductor as inductive reactance. Got it? Inductive reactance, XL. And this is also having just the unit of that of the resistance, and it is what? SI unit is what? Ohms. Got it? So what happened? This E naught by XL. So E naught by XL, it is just like that E naught by R in the case of resistor. Okay, so E naught, the potential difference, peak value to its opposition to the flow of current, that is inductive reactance, that will be equal to the peak current I naught. Got it? And from here, let's try to compare the equation of the instantaneous EMF E is equal to E naught sine omega t, and that of the instantaneous current I is equal to I naught sine of omega t minus pi by 2. Now let's try to observe the phase of these two equations. The phase in the case of instantaneous EMF is what? E is equal to E naught sine omega t, and that of the current is what? Having some difference in the phase here. So in the case of instantaneous current, I is equal to I naught omega t minus pi by 2. So in terms of the phase, when we compare it, current is lagging some angle of what? Pi by 2 from that of the instantaneous EMF. So we said, generally we said that in the case of AC circuit containing pure inductor, what happened? Your AC instantaneous current lags behind that of the EMF by a phase of what? Pi by 2. Okay, so let's try to draw this diagram, and let's try to see how the lagging behind of this current, okay, from that of the EMF takes place. Or in another word, you can also say that instantaneous EMF leads the instantaneous current by a phase of pi by 2 radian in the case of AC circuit containing inductor. Okay, this is how the graph of this instantaneous EMF and instantaneous current, AC current, would have been. Okay, now we started here omega t. When t is equal to 0, what happened? Your sine of omega t will be equal to 0, and so your E will be also equal to 0. That means your EMF will be here. But when I take it that omega t equal to 0 here, then it will be what? Sine of minus pi by 2 is there. Sine of minus pi by 2 is what? Minus 1. So if you take it that minus 1, then it will be minus I naught. So minus I naught will be there. Got it? So what happened when when EMF started from here, then what happened? Your current will be lagging behind that of the EMF by a phase of what? 90 degree. So what happened when I told you that by phasor diagram in the case of resistor, okay, that rotating vector can be thought of what? Rotating in anti-clockwise direction. So when your EMF is somewhere here, your AC current will be at this line. the phases of current will be here, phasor of EMF is here. So when omega t, when EMF, okay, the phasor of EMF is coming up here like this. Suppose if this is your E naught, right, then this angle omega t, okay, then what happen, your current will be also coming little bit like this, okay, your peak current, so that this angle will be also what, omega t. Got it? So if the angle between this peak EMF, okay, this peak EMF and this peak current, the angle between them will be always 90 degree. Got it? When EMF is coming here, for example, okay, peak value of EMF is coming here along the y-axis, then what happen, your peak current will be here along the x-axis, so that the angle between them will be what, always 90 degree. Got it? That is how it is seen with this graph, that the instantaneous EMF and the instantaneous what, current in the case of a circuit containing pure inductor will be having a phase difference of 90 degree. And in this case, what happened, I, okay, instantaneous current, okay, lags behind that of the instantaneous EMF by a phase of 90 degree or pi by 2 radian. Or you can also say that EMF always leads, okay, then that of the current by a phase of pi by 2 radian. You can say in that way also. Now let's try to see the phasor diagram. Okay, see here, this is the EMF, okay, EMF, the instantaneous EMF will be given by its projection onto the y-axis, okay, and your current can be also have that instantaneous current by projecting it along to the y-axis like this. So what happened in this case, your omega t is the phase, okay, initial phase, you can say omega t with this is a reference x-axis, so omega t is there like this, okay, for the EMF is equal to E naught sine omega t, you know it, no? That one sine omega t, so this omega t will be there, but your I will be lagging behind, okay, by a phase of what, pi by 2 radian. So angle between these E naught and I naught will be what, pi by 2, and it will not be drawn along here like this. I naught will not be drawn along this. If I naught is drawn along this direction instead of this, then what happen, we will take it that current is leading the EMF by a phase of pi by 2, but in our case, what current is lagging behind, then that of the EMF by a phase of pi by 2 radian. Okay, now let's see about the AC circuit with capacitor. Okay, capacitor is connected with that of the AC source as shown in the diagram. Okay, and generally I told you that we take it that instantaneous EMF of AC is what, taken as E naught sine omega t. So your E naught sine omega t is here. Now in the case of capacitor, we know that the charge stored onto the plate of the capacitor is expressed as what, BC, okay, charge stored Q will be equal to what, BC. That means its capacitance times the potential difference across the two plates. Okay, but in our case, what happened, the potential difference that is developed across the two ends will be nothing but the instantaneous EMF. Okay, the instantaneous EMF that is given by the source will be nothing but the potential difference across the two terminals. Why? Because this is connected to the source of EMF, so as long as it is connected to this source, the potential difference across this, or the potential drop across the two plates, will be equal to the instantaneous EMF. So instead of the potential, we need to take it as what, instantaneous EMF, so CE, but E is equal to E naught sine of omega t. So you replace it this so as to get that the current, okay, the instantaneous current will be what, a rate of change of flow of charge, okay, rate of flow of charge, we call it as current. So your current can be expressed as dq by dt. So this is just like the differentiation of this given charge with respect to time t. So if you differentiate it, this charge okay, that is differentiation of C E naught sine of omega t, but C and E naught are constant, so you take outside the differentiation and you try to differentiate this sine of omega t. Differentiation of sine of omega t, we know it that is cosine of omega t, right? And if you try to differentiate this phase omega t, I mean rather the angle here, so you will have to have another what, omega, okay? So if you try to differentiate what, your d by dt of what, C E naught sine of omega t like this, then what happened? C and E naught are constant, so we will take it outside, okay, the differentiation, C E naught like this. And if you try to differentiate it sine of omega t, then it will be coming there as what, omega cosine of omega t like this. So differentiation of sine of omega t will be coming cosine of omega t. Differentiation of this angle omega t, again 1 omega will be coming out like this, okay? So but this can be rewritten as E naught divided by 1 by omega c like this, okay? Cosine of omega t in this way. What is this 1 by omega c? This will be called as what, capacitive reactance. So E naught by Xc. In the case of inductive reactance, we denote it by XL, and XL will be equal to omega L. But here this is Xc. So Xc is called as what, capacitive reactance, and it will be equal to 1 by omega c. Okay, so 1 E naught by Xc times of what, cosine of omega t. So this E naught by Xc, this is potential difference by that of the opposition or reactance. So we will call it this as what, your I is equal to, in the next subsequent step, it will be written as I will be equal to what, I naught, okay, I naught. This I naught will be equal to this, got it? I naught will be equal to this, E naught by Xc, so cosine of omega t. So cosine of omega t can be rewritten as I naught, okay, sine of omega t plus pi by 2. So your I is equal to what, I naught cosine of omega t, but this cosine of omega t can be rewritten as I naught sine of omega t plus pi by 2 like this. So that is what I have written here, got it? So what happened when we compare the equation of instantaneous EMF here and the instantaneous equation of this current, I mean instantaneous current, when we compare it, the phase are not same. See, in the case of EMF it is simply omega t, but in the case of current it is omega t plus pi by 2. That means phase is more in the case of current here. So what happened, your instantaneous current leads the instantaneous EMF by a phase of pi by 2. In this case, it is just the opposite of that of the inductor. Got it? In the case of inductor, it was minus there. So current lags in that case. But here, it is plus. So that means your current leads. Okay? Current leads than that of the EMF by a phase of pi by 2. Okay? So let's see how to draw it that. Okay? Now this is all about that of the capacitive reactance and all that I have told you. This is also capacitive reactance and inductive reactance are what, just like the opposition, okay, opposition to the flow of AC current, and their units will be what, in terms of ohms only. It is just similar to that of the resistance in the case of pure resistor, right? Now the diagram, as current leads the EMF by a phase of pi by 2c, when EMF started from this, okay, your current is always reaching its peak value C. Got it? So that means current leads than that of EMF. Okay, or you can say that EMF lags behind. EMF lags behind that of the current, we can say indirectly also. If one is advancing the other, we can say that one is lagging behind than the other, right? In that way. So if a graph is drawn, then the graph would have been in this way. Okay, when this EMF is 0, current already reached its peak value at the very initial time. When EMF is 0, current is already there at the peak. When what happened, EMF is peak, current will be decreasing down here like this. When current EMF is 0, then it will be their peak in the opposite direction. Got it? And in that way, the two graphs of these EMF and what the current can be drawn in this way. So red represents what? Instantaneous current. Blue represents what? Your instantaneous EMF. Right? Let's see about the phasor diagram. Okay, as I told you that this is about that of the peak EMF, and its angle will be what? Omega t. So likewise you can find out the instantaneous EMF. Okay, the projection onto this y-axis will give you the instantaneous EMF. If you drop down a perpendicular line from this peak to the y-axis, then this distance from the origin, okay, this distance from the origin to the peak, to the foot of the projection, I mean, that will give you what? Your instantaneous EMF. Suppose if you drop perpendicular like this, the foot of the perpendicular is here, so this distance from the origin, that will give you your instantaneous EMF E, which will be equal to what? E naught sine of omega t. Similarly, if you drop perpendicular from this y onto the from this peak onto the y-axis, then you will get it the instantaneous what? Current from here like this. The foot of the projection is here, so from the origin up to this, you will get it that instantaneous current. Got it? So from this phasor diagram, we can easily see that your current is what? Leading the EMF by a phase of how much? Pi by 2 radian. Got it? Now let's see about this variation of this reactance with the frequency. Let's take up first about the inductive reactance. Okay, we know that I is equal to E naught divided by omega L. Okay, then what happened? Your I naught, the peak value of the current, is equal to what? Ratio of the peak EMF to that of the inductive reactance, omega L. So your omega L is nothing but we call it that as inductive reactance, and it is denoted by XL. Now this XL is inductive reactance, and omega, we know that omega is equal to what? Twice pi by t, right? Omega is equal to what? Twice pi by t, right? So omega is equal to what? Twice pi by t. What is this? Capital T, this is a time period, and 1 by t, we know it that is equal to frequency. So if you try to write it, then this will happen like this, twice pi by 1 by t. What is this 1 by t? 1 by t is nothing but this is the frequency. Reciprocal of time period is frequency. So we can write it that as twice pi f like this. So your omega will be equal to twice pi f. That is what I have written here. Okay. So that means if you try to correlate this inductive reactance with this frequency, other 2 pi L, these are all constant for that particular inductor. So if you try to correlate this inductive reactance with frequency, then it will be what? X L is directly proportional to frequency. So if you try to draw a graph between what? The inductive reactance with the frequency of what? Frequency of AC source, then it will be what? Directly proportional. And so we know that for directly proportionality, the graph would have been what? Always been a straight line passing through the origin, right? So let's see about the variation of the capacitive reactance with frequency. Why? Because your capacitive reactance XC can be also related with frequency. Why? Because Xc is equal to 1 by omega c, right? So here it is Xc is equal to 1 by omega c. So omega means what? Twice pi f, as we have done. So what happened? Your capacitive reactance is inversely proportional to the frequency. So we have to draw it, the reciprocal graph. Okay, in the reciprocal graph it is curved downward like this. Got it? So in the case of inductor, if frequency increases, its inductive reactance will increase correspondingly. But in the case of capacitor, what happens? If frequency of the AC source increases, then what happens? Its capacitive reactance will be what? Decreasing. Got it? So with that, we will come to the end of this second part of the video. In the next part, we will try to see the remaining portion of those of LCR circuit and all. Okay, thank you.